This video was brought to you by GeneralPAC.com, making power systems intuitive, open, and free to everyone, everywhere. Consider subscribing and supporting through patreon.com/GeneralPAC. This is the mechanism for you to support us financially so we can continue making high-quality power system video tutorials. Our corporate sponsor for this topic is AllumiaX.com from Seattle, Washington. Contact them for industrial and commercial power system studies. Fault analysis using waveforms. In part 1 of this series, we're going to do something just a little bit differently this time. And in this series, we're going to look at a particular article by Schweitzer Engineering Labs. The author is David Costello, and the article is called Event Analysis Tutorial, and we'll be going over this particular tutorial. There's part 1, and in part 1 it lays out the problem statements, which has several examples of fault analysis, and then part 2, which is this part right here, it essentially gives us the key. So we're going to be going over both parts, and they are publicly downloadable. So you can just search for Event Analysis Tutorial and then search for this author, and you should be able to get this PDF. So in the first part, we're going to be analyzing this particular waveform, and the introduction for this particular waveform is that it's a distribution feeder fault, and in here it says the event occurred on a distribution collector at a wind farm, and for practical purposes, fault on a collector behave like faults on a radial feeder fed from a Dy1 transformer. Okay, a Dy1 transformer is our standard delta Y transformer connection, where the low side reference quantity lags the high side reference quantity by 30 degrees. So it's our typical delta Y transformer connection in the United States. The wind turbine do not contribute any significant fault current. The location and connection of the potential transformer PTs are unknown at the time of the publication. So a lightning arrestor, one per phase, are positioned on the top of the steel supported structure. Each arrestor is connected by a jumper to a phase conductor. A bird caused a fault near one lightning arrestor, which caused its jumper to blow loose and contact other phases, right? So a bird came in the line, which causes a fault, and that causes a jumper to blow and blow loose and make contact with other phases. So that's kind of the situation that's in hand. And what we end up getting through the relays is this particular fault. And the question that the author asks is, before the fault, in what direction is power flowing? What is the power system phase rotation? What type of fault occurred? What protection element within the relay caused the trip? How long did it take for the relays to operate? How long did the breaker take to clear the fault? Did the relay and protection system operate correctly as designed? So let's go through and let's analyze this event and answer those questions one by one. So the first question, of course, is before the fault, in what direction is power flowing? And so the easiest way to answer this question is to look at the event before the fault had occurred, and the inception of the fault is essentially at this particular point here. And we can see that the waveforms are positioned like this, and we're looking at the voltage waveforms here. So this is the voltage waveforms. This right here are our current waveforms, and we'll talk about it in a little bit more detail. These right here are our sequence component magnitudes, and these guys right here are our digitals. And so from the waveforms itself, it appears like power is flowing into the bus or in the reverse direction. And the second question is, what is a system phase rotation? And we could actually zoom in, and let's zoom in into the voltage waveforms. What we find is that the voltage waveform essentially starts with the purple, and then it goes into this greenish color, and then it's this teal color. So if we look at our map, the purple represents phase A voltage in kilovolts. The teal color, the greenish color, represents the phase B voltage in kV, and then the teal color represents phase C voltage in kV. So here we know exactly that this right here is A, then it's B, then it's C. So the phase rotation is essentially an ABC phase rotation, and we look at it by, we look at the voltage waveforms before the fault actually occurred. And the inception of the fault is essentially this dotted blue line right here, right? So let's look at the second question. The third question is, what type of fault occurred? So there's a lot going on in here, and we would really have to look at this holistically. So initially, of course, we want to start from before the fault and make sure things are good. Make sure that we understand exactly what's going on here. So we have a good balanced system before the fault occurred, right? Phase A, B, and C voltage quantities are pretty well balanced, meaning that they are equal magnitude and they're 120 degrees apart from each other. And even though we won't be able to see it here, but there are, there should be some load current on our phase current quantities or current waveforms. So in the pre-fault area, we have good balanced voltages, and we have some load current that we can see and visually verify. So at the inception of the fault, which is this blue dashed line, what we see is that we see a huge presence of this particular waveform on the current magnitudes, right? And it's like greater than 10,000 amps of phase current. And by the color of this waveform, we see that it's the green color, so it must be phase A current, right? So we see a huge presence of phase A current, whereas the other phases, phase B and phase C current, at this point are pretty darn small. So we could immediately tell that this appears to be a phase A to ground fault, right? And another way to confirm that is by looking at the voltages. So what we see when we have a phase A to ground fault, we should see a huge depression on the faulted phase. So over here, we see immediately that the voltage, the purple, which is phase A voltage quantity, the purple waveform actually is depressed, as we can see. So we kind of confirmed that the phase A current has a high magnitude, phase A voltage is certainly depressed, and so this certainly is a signature, a classical signature for a phase A to ground fault. And even on the voltages, we can see that the remaining phase, meaning phase B and C, are relatively intact. They're definitely depressed, but the phase rotation are relatively intact, meaning it's purple, then green, then teal. So it's purple is depressed, then green, then teal, right? So relatively intact. But then at this particular point here, something happens, right? And this is where the fault is actually transformed into a different type of fault. And what we see is there's another phase current that is prominent, and that current is your blue current. So it's phase B current that becomes prominent, and so it may be a two-line, or it may be a line-to-line fault with phase A and B current that are prominent, or it could be a line A to B to ground fault, meaning A, B, and ground fault. Now, one of the signatures for a line-to-line fault is that when we're looking at the current quantities, we should expect the phase A current and phase B current to be equal magnitudes but 180 degrees apart. And we don't see that here. They may be close to equal magnitude, but they're certainly not 180 degrees apart. Meaning if they were 180 degrees apart, then this peak for phase A current would match another peak down here for phase B current, and we don't see that. So what this appears to be is a to B to ground fault, right? And we could look at the voltage quantities to also confirm that. So at this particular point, when the fault changes, we see a depression on both the purple, which is the voltage waveform, and as well as the green, which is this voltage waveform here. So both the purple and the green right here, there's a voltage depression there, and the teal is the phase C voltage. So that is depressed, but not as much as purple and green, which is phase A and B voltages. So so we can confirm right here that this is a two-line to ground fault. And then as we get closer towards the very end, we can see that all three phases are involved, which means that this is more like a three-phase fault, meaning phase A, B, and C fault. And we can see in the voltage waveform, again, all three waveforms are depressed quite a bit. So this is definitely toward the very end, it becomes a three-phase fault. And towards the very last piece right here, what happens is that the current waveforms goes away, right? And the voltage waveforms become balanced again. So what this is telling us is that the fault is eliminated through a breaker. So the breaker opens up and isolates the fault, and we get a restoration of the voltage. Voltage goes back to normal. So that's what this is telling us, right? And so we can look at the answers, but let's continue with the questions. What type of fault occurred? We kind of answered that. What protection element within the relay caused the trip? So let's look at these guys right here. Now, before we look at the digitals, I do want to comment on the sequence components part of it, right? So again, the sequence components are the gray, the green, and the red. So gray is the zero sequence current magnitude, the green is the positive sequence current magnitude, and the red is the negative sequence current magnitude. When it's a line to ground fault, we can see that both all three positive, negative, and zero sequence currents are moving together, and they're relatively equal. That is what makes sense. When there's a one line to ground fault, the positive, negative, and zero sequence current should be equal in magnitude. And then towards when the fault became a two-line to ground fault, then we see a difference in positive, negative, and zero sequence currents, meaning that there are non-conforming values. There are three different magnitude quantities for positive, negative, and zero sequence current, right? And they continue to be. We know that this occurs for a two-line to ground fault. And towards the end right here, when it becomes a three-phase fault, we see that both the gray and the red drops out, meaning the zero sequence current and the negative sequence current kind of drops out when it becomes a three-phase fault, but we see a continuing rise of the green, which is the positive sequence current magnitude. We see a rise in that. So what this is telling us is that it becomes a three-phase fault in which the phase currents are relatively balanced, which means we'll get a drop off of the zero sequence current and the negative sequence current because they are measuring the unbalance in our phase sequence. We see a continuing rise of the positive sequence current, right? Because it becomes a balanced circuit, and with a balanced three-phase fault, we would normally see a high positive sequence current magnitude. So from a sequence components perspective, this makes complete sense, right? And so let's look at the digitals now. And the question was what protective element it tripped on. So this is a trip signal right here. And so what this is telling us, the first one, the trip signal, is that the trip element did not assert until the more of a bold line right here. So this at this point right here, this is what is telling us that the trip signal within the relay asserted, right? And it kept on asserting until the end of the waveform. And then this 52A contact, the 52A contact tells us the breaker position, whether or not the physical breakers are actually in the open position or the closed position, the contacts are. So what this is telling us is that the breaker is closed, meaning it's a bolded line, and the breaker continues to be closed until this particular point. And then the 52A contact drops off, which means it becomes 0 and the breaker is actually open. So the breaker opens at this particular point here. The 67P2T element, if we look at the relay manual, which is described within this particular article, this 67P2T, the 67 element is a directional overcurrent element, and then P2, P means it's a phase element, and this 2 means it's a second element. There's 67P1 and there's 67P2. So P2 just means that it's a second element, second set. And this T right here means that it actually timed. So it's actually, timed and tripped. So so what this is telling us, this line right here, is that it didn't pick up, meaning it's 0, it continued to be 0 until this particular point, and then the 67P2T actually asserted and it became 1. And so this right here is what I believe the tripping signal for the relay. So the 67P2 element is actually the element that tripped the breaker, right? And then the 50P2, 50 is an instantaneous element, P is the phase. So this, as you can see, is deasserted, and then it gets asserted here, and then it continues to be asserted until right here when all of the currents are actually dropped off. So this is probably some sort of indication that you have a fault above a certain, or the current is above a certain threshold. So the 67P2 is the element that actually tripped, that caused the trip. And then how long did it take for the relays to operate, and how long did the breaker take to clear the fault? The blue line indicates that the fault is triggered, right? The fault triggers, and we know it's the 50P2 element is picked up, right? And so when the relay actually sensed that it was a fault, it was at this particular point right here, right? And that's the element that tripped it. So from here to here is actually 15 cycles. So it took 15 cycles for the relay to detect and operate one of its protection elements and told the breaker to actually open up. And how long did the breaker take to open up? Well, it would be after this signal here, and between this and the 52A contact dropping off, which is this right here. So the difference between these 2 points is approximately, I would say, 3.5 cycles. So it took the breaker 3.5 cycles to actually clear the fault, which makes sense, and it's a common value. So how long did it take for the relay to operate? Approximately 15 cycles. And how long did the breaker take to clear the fault? And this was approximately 3.5 cycles. Did the relay and protection system operate correctly as expected? So I would say yes, the relays and the protection system operated correctly as expected for this particular design. So I hope this was useful and enlightening. So let's look at the key, the answer key, which is part 2 of this tutorial, and see what it's telling us. So for question A, but it said before the fault, in what direction is the power flowing? Power is flowing into the bus or in the reverse direction. For part B, what is the system phase rotation? And we said it was ABC, and it is actually ABC, and we verified by looking at the pre-fault voltage waveform. What type of fault occurred? This is an evolving fault on the feeder, forward direction. It starts as a to G fault, which is phase A to ground fault, evolves into an ABG fault, which is phase A to B to ground fault, and then finally evolves into a three-phase fault, which is in this particular direction, in this particular area here. So this is all correct. What type of protection element within the relay caused the trip? 67P2T, a non-directional phase over current definite time delay element. So I'm not sure what this means, non-directional. 67, if you look up what the ANSI device number for 67 is, it's actually a directional element. So I'm not sure whether or not this is a typo, but regardless, it's a phase over current definite time delay element that actually operates. And it's it's interesting to note that this is a definite time delay, right? And definite time delay is a element that has to wait a certain amount of time before tripping action could occur, and it appears from how long the relay actually waited that the time delay is 15 cycles. So the relay detected the fault, but because there was a 15 cycle delay, it waited that long before it could issue the trip. How long did it take for the relay to operate? 15 cycles. And how long did the breaker take to clear the fault? And we said about 3.5 cycles, which is what this is also says. So, and did the relay's protection system operate correctly? And that was yes. So I hope this was useful and this was enlightening. So we'll continue to go through this particular article in this particular tutorial by Schweitzer Engineering Laboratories, and David Costello is the author. Thank you.